Zeal Education Society, redefining excellence.
Hello friends, my name is Chinmay Deshpande. I am from Department of Electrical Engineering, belongs to Zeal College of Engineering and Research, Narhe, Pune. In this video lecture, we are going to discuss about speed control of a DC shunt motor. Now we know that what is a back EMF EB? The back EMF EB of a DC motor is nothing but whatever EMF which will be induced in the armature conductor due to the rotation of armature in a magnetic field. Therefore, the magnitude of a back EMF, that is EB, can be given by a EMF equation. Already in a previous video we derived EMF equation of a DC motor. It is given by EB equal to NP phi into Z upon 60 into A. This is your equation number 1, where P is the number of poles, phi is flux per pole, N is nothing but speed which will be measured in RPM, Z is nothing but number of armature conductors, and A is nothing but parallel paths. But we also know that this EB equal to V minus IARA. This is what is the equation for a DC shunt motor. Treat this equation as a equation number 2. Therefore, from equation number 1, we can write a formula for a speed, that is N equal to EB into 60 into A upon P into phi into Z. Treat this equation as a equation number 3. But we know that for any DC motor, it may be series or a shunt. A, that A is nothing but parallel paths, P, that is number of poles, and Z is nothing but number of armature conductors. All these parameters are constant. So therefore, we can modify this equation number 3 as N is directly proportional to EB upon phi. Why? Because 60 is constant, A is constant, P is constant, and Z is also going to be constant. So your speed is directly proportional to your back EMF, and it is inversely proportional to the flux per pole. Now from this equation, N is directly proportional to EB upon phi, that is from equation number 4, and from equation number 2, EB equal to V minus IARA. What we will do, we will substitute this equation number 2 in place of EB for equation number 4. So here your equation of N is N directly proportional to V minus IARA upon phi. Now this equation gives you relationship of a speed with respect to supply voltage V, with respect to armature current IA, and with respect to your field flux, or which is also called as a flux phi, which will be produced by the field current. So therefore, in all there are 3 methods. Either by controlling a value of armature resistance RA, we can control the speed. So this method is called as armature resistance control or a rheostat control. Second, by changing this field flux phi, we can have a control over a speed. So this method is called as field flux control. And third method is by changing the supply voltage V also, we can have a control over a speed. So this method is called as armature voltage control method. Now let's discuss the classification of a speed control of a DC shunt motor. There are 2 main classifications. First is armature control method, second one is field control method. Now in armature control method, we have 2 methods, that is armature resistance control, controlling a value of RA, and armature voltage control. And in case of field control DC shunt motor, we have only one method, which is called as field flux control. Now let's discuss each and every method of a speed control of DC shunt motor one by one. First will be resistance variation in armature circuit. Now this method is also called as armature resistance control or a rheostat control. Now this is what is a figure for a speed control by using armature resistance control. Now here you will observe that V is the voltage which is given, RA is the armature resistance, this will be your armature, this is RSH, that is your field winding, SH, why SH is given? Because it is shunt connected, so this is shunt connected field winding. Now here you will observe that external resistance RE is connected in series with armature resistance RA to the armature. So in this case, the field is directly connected across the supply, and therefore the flux phi is not affected by a variation of this external resistance RE. Whatever voltage drop in RE it reduces the voltage which will be applied to the armature, and therefore the speed is going to decrease. How? Let's discuss here. Let's we have a simple diagram of a DC shunt motor. Here you will observe that V is the voltage which is given to both armature and the field winding. I is the current which will flow. This I or IT is the total current. Now part of the current will flow through this armature, so this is your IA. Part of the current will flow through the field winding, which will be IF. RSH is nothing but a shunt field resistance. EB is the back EMF and RA is the armature resistance. So therefore, for this armature winding circuit, we can write an equation as whatever voltage which is applied V equal to EB plus IARA. Now from this equation, we can write the equation for EB and treat this equation as equation number 1. So EB equal to V minus IA into RA. Now let's substitute few values for getting a value of EB. Let here we have considered supply voltage V is 240 volt. Then IA, that is armature current, is 10 ampere. RA, that is armature resistance, is 0.01 ohm. So by substituting all these values in equation number 2, we will get the answer for EB equal to 239.9 volt. Now let's take another diagram which includes this external resistance RE is connected in series with armature resistance. So therefore, whatever equation for the armature is V equal to EB plus IA into bracket RA plus RE. Why RA plus RE? Because here we have connected external resistance in series with armature. So from that we can write the equation for EB, which is equal to V minus IA into bracket RA plus RE. Now again we will substitute here few values. Suppose again the same values we have taken. V equal to 240 volt, IA is the 10 ampere, RA armature resistance is 0.01 ohm. Now whatever external resistance connected here in series with armature, treat this value as a 5 ohm suppose. So by putting all these values in above equation, we will get the answer for EB equal to 239.5 volt. So here you observe that after connecting external resistance RE, your value of EB is going to decrease, and we know that N is directly proportional to EB upon phi. So whenever your EB decreases or increases, your speed also increases or decreases. Here the large amount of a power, that is IR, is wasted in the external resistance RE. That is, this IA into RA plus RE is nothing but a lost power. Now here again we will discuss N directly proportional to V minus IARA upon phi. This is a formula. So in a case 1 already we discussed that EB was 239.9 volt. In a case 2 it was 239.5 volt. So therefore, as here whatever value of a flux phi, it also going to change, but the change in the flux phi is very less compared to that of change in the EB. So therefore here we have a direct control of EB on speed, that is N. So N is directly proportional to EB, which is directly proportional to V minus IARA. So therefore, as your EB value is going to reduce in the case number 2, that is whenever we connect external resistance in series with RA, so therefore speed is also going to reduce. Now here what are the drawbacks associated with this method? First one, after connecting external resistance, your drop in the power will be large. So a large amount of the power is wasted because of connection of external resistance RE in series with armature resistance RA. Then this armature resistance control is restricted to keep the speed below the normal speed. Why? Because in the case 1 it was 239.9 volt, whereas in the case 2 it was something 239.5 volt. So here after connecting this external resistance, your EB is going to reduce, and as your EB is going to reduce, your speed is also going to reduce. So this method is used to control a speed below rated speed, and above rated speed or above normal level it is not possible to control the speed by this method. For a given value of RE, that is external resistance, the speed reduction is not constant, but it varies depending upon what type of a load which is connected to the motor. So this is what is about armature resistance control or a rheostat control. Let's discuss a second method, that is variation of a field flux phi. Now this method is also called as a field flux control method. Now already we know that the field current is responsible for a production of a flux, and therefore if we have a control over a field current, but obvious we can control on the flux also. So this is what is a figure. Here you will observe that in series RC, that is external resistance, is connected to the field winding. This is your field winding resistance RSH. Again V is the supply voltage, RA is nothing but your armature resistance, back EMF EB will be there. This is your motor or armature, and the supply is given as it is a shunt motor, so the same voltage is applied to both the armature and field. Now here the speed can be controlled by connecting a variable resistor RC in series with a shunt field winding. Now here, to control the flux, the rheostat, that is a variable resistor RC, is to be added in the series with the field winding, and because of that there will be increase in the speed. Why? Because of the flux. Here flux is going to decrease. So the field current is relatively small, and therefore whatever power loss, that is I square R loss, it will be decreased here. Now let's see, this is a simple diagram. Already we discussed this diagram in a previous speed control method. Now whatever equation associated with field circuit is nothing but voltage V is nothing but ISH into RSH. Now you will ask me question, sir, what is ISH? The field current IF and ISH both are same. This is what is a different nomenclature here I have used. So V is the supply voltage, ISH into RSH. So from that I can write an equation for a current, that is ISH equal to V upon RSH. This is what is a normal case whenever we have not connected any variable resistor in series with a shunt field winding. But let's take a second example. Suppose here if we have connected this RC variable resistor in series with this RSH, then what is your equation of a voltage for this field winding? V equal to ISH into RSH plus RC. So therefore from that what I can write, ISH equal to V upon RSH plus RC. This is your equation number 2. So now if you observe these two equations of current, that is shunt field current, you will observe that after connecting your external resistance RC in series with RSH, by keeping your voltage constant, the value of ISH is going to decrease. As your value of ISH is going to decrease, so but obvious what happens, your field, that is our flux, that is phi, is also going to decrease, and as phi, that is flux, decreases, your speed will be increased. So therefore this is what is the relation that we obtain from this formula. As phi decreases, your N is also going to increase. Now let's discuss advantage associated with this method. But obvious this method is easy and convenient. Now here whatever shunt field winding is there, it is very small, and therefore the power losses associated with this shunt field winding is also less. And what are the important points again related to this method? Here the flux cannot usually be increased beyond a certain limit. Why? Because if the flux is increased beyond a certain limit, there will be a saturation of an ion, and therefore this speed control method is limited up to weakening of the field, which gives an increase in the speed. So here you observe that as your phi is going to decrease, your N is also going to increase. So therefore this method is used for controlling the speed of DC shunt motor above rated speed. Again, it is applicable only to a limited range. Because of the field is weakened too much, there will be loss of stability. So this is what is about field flux method, that is phi. Now let's discuss variation of applied voltage. Now this method is also called as armature voltage control method. Now here what we have to do, already we discussed that relationship between speed, then voltage, then armature resistance and the flux phi. N is directly proportional to V minus IA RA upon phi. So here if we try to control the value of a voltage V, then we can control speed N. So here this is what is a figure. Here you will observe that this will be your DC generator, this will be your motor, the load is connected, and this will be your field windings. So this is a motor generator, that is MG set, and this is DC drive set. Now this speed control method is also called as Ward-Leonard method, and it was introduced in 1891. Now let's discuss in detail what this figure is. Now in the above system, this M is nothing but a motor, that is main DC motor, whose speed is to be controlled, and this G is nothing but a generator. Now already we discussed that what is the difference between generator and a motor. If we say from construction point of view, both are same, but the difference depends upon whatever value which is given as an input or the output. Here in case of generator, here you will observe that 3-phase AC supply is given as an input. So whatever output which will be generated is the electrical energy. Now that same electrical power is given to a DC motor here. Now here we can control the magnitude or the value of output voltage which is to be obtained from a DC generator by controlling this 3-phase AC supply. So here this 3-phase generator, whatever generator is there, that generator is that generator here 3-phase AC supply is given, and it may be, you can say that the driving motor, it may be an induction motor or a synchronous motor, this AC motor which is to be written here. The combination of an AC driving motor and a DC generator, that is, this is the combination, this combination is called as motor generator, that is MG set. Now here, whatever voltage of the generator, that we are going to change by changing this supply. So whenever the voltage is changed, the same changed voltage is given to a DC motor here. Here the voltage of the generator is changed by changing the generator field current. This voltage, when directly applied to the armature of this particular DC motor, the speed of the motor also changes. Now here the motor field current is IFM. Here IFM, F is the field, M is the motor. So motor field current, this is your motor, so this will be your motor field current, IFM is kept constant, so that the motor flux, that is phi m. Now we know that this flux is produced because of this IFM only. So as your IFM is constant, your phi m is also going to be constant. And while the speed of this motor is controlled, the motor armature current IA is also kept equal to its rated value here. Now here N is directly proportional to EB upon phi. So if we have a control over the voltage, then we have a control over speed also. Now here you will observe that in this case, the generated field current, that is IFG, is varied in such a way that the armature voltage Vt changes from 0 to its rated value. As we have a control over this voltage Vt, and this controlled voltage, increased magnitude or decreased magnitude can be given to a DC motor as an input, then only we can control a speed of this motor. The speed will change here from 0 to the base speed. Now as the speed control is carried out with the rated current, armature current, that is IA, and with a constant value of a field flux phi m, a constant torque will be produced. That constant torque is directly proportional to only current, because already we discussed a torque equation of a DC motor. T is directly proportional to phi into IA. So therefore the field flux up to rated speed is obtained by this method. Now here you will observe that whatever the product of the torque and the speed is nothing but a power, and it is proportional to your speed. So therefore with increase in the power, the speed will also increase here automatically. Now let's discuss few advantages of Ward-Leonard drive. Smooth speed control of a DC motor over a wide range in both the direction is possible because of this particular method. Then it has inherent braking capacity. Then uniform acceleration will be obtained because of this method. Now what are the disadvantages associated with it? Here, as separate generator is required for controlling input voltage for the motor, so therefore the total assembly has a larger size and its weight is more. Here the initial cost will be high because but obviously we have used here motor generator set, and therefore the motor generator set installed of the same rating as that of a main DC motor, hence cost increases. Then maintenance of the system is a frequent in this case because of this motor generator set. So this is what is about a speed control method by using applied voltage. Now, what are the applications of a Ward-Leonard drive? Here, this can be used where the smooth speed control is required. Now, where it is to be required? First example is a rolling mills, where we require to have a smooth control. Then elevators, cranes, paper mills, diesel electric locomotives, and the mine hoist. So, if you want to control the speed of all these, then specifically here we use Ward-Leonard drives. So, this is what is about a speed control methods of a DC shunt motor. So, in this video, we discussed three important methods: resistance control, that is armature resistance control, then field flux control method, and this is armature voltage control method. Thank you.
Zeal Education Society, redefining excellence.